Let's take stock of what we've learned about the structure of atoms and their primary components. Atoms have a heavy nucleus comprised of protons and neutrons surrounded by a cloud of light electrons. The number of protons in the nucleus gives atoms their identity, but we will see that it is the electrons that matter the most when forming molecules. The electrons cluster around the nucleus in energy shells, and the outermost shell, the valence shell, is most stable when it is full. This is the octet rule. This rule will be the key to understanding bonding between atoms, especially for the lighter elements near the top of the periodic table. In the lessons of Module 2, we will see that there are a couple of different ways that atoms can satisfy the octet rule. This results in molecules, atoms held together by strong attractive forces called chemical bonds. The bulk of this module is devoted to discussing how these molecules form and how we can identify them using formulas, names, and structural diagrams, and how we can distinguish two different molecules that have the same set of atoms. So how can an atom satisfy the octet rule? One way is by adding or subtracting electrons to form ions, which have a net electric charge. As we learned in Module 1, charged particles experience electrostatic forces, which can attract them strongly to one another. This is the basis of ionic compounds, and we observe it in such substances as table salt, rust, and many minerals found in nature. We will learn how to predict the ratios of the elements in some simple ionic compounds and express their empirical formulas. Another strategy that atoms use involves sharing electrons with one another so that both achieve a filled valence shell or octet by forming a covalent bond. We will examine how to determine the capacity of a given element to form such bonds and study several instructive examples of two atoms bound together to form diatomic molecules, such as nitrogen and oxygen that make up most of the air we breathe. Love those diatomic molecules. Many elements, particularly carbon, have sufficient bonding capacity to form bonds to several other atoms at the same time. As a result, one can form molecules of many atoms, so-called polyatomic molecules. And you will see that there are some consistent structures that we can use as building blocks to form more and more complex arrangements of atoms. In fact, there is an infinite variety of what can be made. Without this, the universe would be a dull place indeed, but with extreme molecular complexity comes the possibility of living things. It will be necessary for us to develop a common means for labeling or naming the covalent molecules we encounter. Without such a system, we would be left saying, you know, that molecule with the oxygen that forms a double bond to a carbon and also has a couple of hydrogens attached. Instead, we can refer to it by name, formaldehyde, or by formula, CH2O, and save ourselves a lengthy explanation. You will discover that different ways of representing molecules have different advantages and disadvantages, and some are even ambiguous. We will close Module 2 by considering how to distinguish between two molecules that have the same atomic composition, but display different physical and chemical properties. These are called isomers, and you will learn how to recognize pairs of isomers and determine how they differ from one another structurally. This module lays the foundation for all our future explorations. The material should not be difficult for you, but it is essential that you develop a thorough understanding of these concepts so that we can elaborate on them further in subsequent modules. The concept of isomerism is particularly useful, and we will see that it has many variations and consequences. So let's get started.